Welcome surfers, this is Joel and this is Rustlers Atom 2.1. In today's video we talk about ownership in Rust. If you haven't subscribed to this channel yet, maybe this is the right time to do it. So we can start. Ownership is the Rust's answer to memory management. It replaces the garbage collector found in languages like Java or Python, and it replaces the manual memory management found in languages like C or C++. Ownership is a compile-time bookkeeping system based on one simple law. Every value has exactly one owner, and when that owner goes out of scope, the value is simply dropped. That's it. The rule is very easy to understand. Let's start with the smallest possible example to see this law in action. I can create a closure like this. Inside this closure I declare x equal to 42. Perfect. Inside this closure I can print this, the value of this variable. So print line for example, I don't know, x equals to something and x. Perfect. The variable x owns the value 42, and as long as we are inside the curly braces, x is valid. However, the moment the this inner block ends, x goes out of scope, so Rust immediately releases the storage. If you try to use x after the closing brace, the compiler will stop you 100%. So if I write another print outside the curly braces, maybe an identical print x, okay, as you can see, the compiler say that x not found in this scope. We now simply comment out this line and our little program print the value 42. The ownership can move, and this is different from many other languages where assigning a specific variable create a copy of this variable. If I create an owned string, for example s1 equal to string from hello, so in this case s1 owned the string hello. Now I create another string s2 equal to s1. When we assigned s1 to s2, the ownership moved, so I can simply try this with a print line. Okay, s string is something s1. Let's say if I can compile this code. As you can see, the value borrowed after move. So the value is moved here and is not available inside the print line. If I write S2 here, the compiler have nothing to complain and print the value. The same logic applies to a function. For example, I can write two different functions. The function consume I32, okay, vec I32, and the function makeVec that return a vector of I32. I can create on the fly a new vector 10, 12, 13 and return it in this function, and I can print with debug formatting, so in this way, or numbers vector. Okay. I have two different functions. Now inside my main function I can create a new vector to try out my consume function. So vec is equal to 1, 2, and 3. And I can move the ownership of this vector inside the consume function. Okay, there are a warning about that code, but the script works with any problem. But with this call to consume function, I move the ownership. So if I try to print again my vector, in this case the compiler complain about the use of a variable that was moved to a function. As you can see, value borrowed after move, because if I consume my vector, the value is moved inside the function, and at the end of the function the compiler simply free this memory. So now I simply comment out this line. Okay, and we can do the opposite thing with the other function, the makeVec function. So create a new vector with makeVec function. With this call we move the ownership of the vector out of the function. So in this specific case I can print the value of the vector, because now the vector is owned by W. Okay, also with debug notation W. Okay, and now I think that the compiler have nothing to complain. Perfect. So as a recap, V in these two lines is moved into the consume function. So once consume finishes, V is simply dropped. It not longer exists inside the main, so this code can't be executed. Make vec create a vector and do the opposite thing, so passes the ownership to W. In this case, the value of the vector is a variable inside my main, and so I can print the value with this line, with the print line. You might notice that some values don't behave in this specific way. Integer, for example. Integer in Rust behave like they do in C. So if I write another example, let integer 1 equal to 5 and let integer 2 equal to integer 1. In this case I can print both are fine. So if I write integer 1 and integer 2, the compiler have nothing to complain and is able to print both value. But why this behavior? This is because simple scalar types like integer in this case, or booleans or chars, implement a trait, the copy trait. They are small fixed size values that live on the stack, so copy them is incredible cheap. For this reason, in Rust, all these small types implement the copy trait. The focus of the next atom will be the clone trait and also the copy trait. So for this video it's all. See you in the next atom, and don't forget to follow, to like, and to keep your thinking cap on.